In today's lesson, we are going to continue our review of factoring by looking at some special cases. Now, the cases that we looked at, you are able to factor them using the methods that we looked at previously. So those are the simple trinomials, or the common factoring, or the complex or tricky trinomials. But sometimes we can kind of do it a little bit quicker by recognizing some of these special cases or scenarios. So the first one we're going to look at is what we call a difference of squares. Now, a difference of squares, or a difference of squares polynomial, is exactly as it kind of says. It's a difference or subtraction between two perfect squares. So what we do is we look to factor a difference of squares when we see two terms separated by subtraction. So generally speaking, as long as we see two terms and there's a subtraction, chances are that it's this situation, a difference of squares. If not, and again, we'll look for what, we'll kind of do a couple examples to see what to look for. If it doesn't factor like that, then all you can really do is common factor. A couple of things to keep in mind, right? What is a perfect square? Well, a perfect square is a number that when you square root it, you get a nice answer or a nice value. So for example, 9 is a perfect square of 3 times 3. 4 is a perfect square of 2 times 2. 1 does work. It's a perfect square of 1 times 1. So again, we can think of all these numbers. What's 4 times 4? Well, that's 16. So 16 is a perfect square as well. We could do 25. 5 times 5. Right, so we can think of all those different numbers. 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, and so on. It also appears with variables. X squared is a perfect square of x times x. Or it could be a to the power of 2, anything to the power of 2. Same thing if it's to the power of 4, because that could be x squared times x squared. X to the power of 6, that could be x cubed times x cubed. So when we're dealing with variables, we're looking for even number exponents. Basically, does the exponent divide by 2? So again, that's kind of what we're looking for when we talk about a perfect square. Now let's look at a couple of examples of how we get to that. So we're going to expand and simplify the following polynomials. So we're going to use our distributive property that we've talked about before in our previous lesson. So x times x, x times negative 3, 3 times x, and 3 times negative 3. Here we get x squared minus 3x plus 3x minus 9. When I go through and collect my like terms, I see that my two middle terms are like terms. However, I should see now that when I go to collect them, minus 3x plus 3x, they cancel each other out. So they cancel each other out. I'm just left with x squared plus 9. So this is an example of a difference of squares. We see x squared, which is a perfect square, and we see 9, which is a perfect square, and they're subtracted from each other. So this is the difference of squares. This is what it looks like down here in the polynomial form, you might say. And up at the top here, that's the factored form. That's what we want to get to. So here we're just doing our multiplication just so we can kind of see where these difference of squares come from. If I look at b, I'm going to multiply and do the same thing. Distributive property, 2x times 2x is 4x squared, 2x times 3 is 6x, minus 3 times 2x is minus 6x, and minus 3 times 3 is minus 9. Again, we want to collect our like terms, which happen to be the two middle terms, but because they're just opposite signs, positive 6 and negative 6 cancel each other out. So we're left with 4x squared minus 9, which is a difference of squares as well. And finally, looking at the last one, 3x times 3x, 3x times 5y, negative 5y times 3x, and negative 5y times 5y. So after that distributive property, we get 9x squared plus 15xy minus 15xy minus 25y squared. So if I look to cancel or combine like terms, I should find, and the two middle terms are the same, or not, they're the same values but opposite signs, they cancel each other out. So all that I'm left with is 9x squared minus 25y squared. So again, this isn't factoring, this is just multiplying, but we're trying to see where we get, or where this kind of pattern comes from. Where do we get a difference of squares from? What's the relationship? Again, hopefully we should see at least what a difference of squares look like and what the original form is, or the factored form, because we're going to use that relationship to help us factor. So to factor a difference of squares, two key things. Again, making sure we recognize it first, and then once we recognize that we have a difference of squares, I look at the first term and I square root that. So this, and that goes in the first part of my bracket. So essentially a is actually the square root of a squared, and that's the same in both brackets. The second term in our brackets comes from the second term in our difference of squares, and that is the square root of b squared. B is just the square root of b squared. That's our second term. And the other piece is that we have one positive and one negative, one addition and one subtraction of terms in our brackets. So that's really what we're looking for, is recognizing what the square root of our perfect square is, and then just putting an addition and a subtraction. So let's look at some examples. P squared minus 9, well, let's check. Do we have a perfect square? Square root of p squared is p. Square root of 9 is 3. So we do have we have two perfect squares. They are separated by a subtraction here. This is a difference of squares. So that means I'm going to have two sets of brackets. P in the front, 3 in the back, P in the front, 3 in the back, and then just one's addition and one's subtraction. And that's it. So that's all we have to do to factor a difference of squares. If I look at b, let's take the square root of our two numbers. It already fits the idea of the fact that we have two terms, their subtraction. Now we're just checking to see if it's a difference of squares. So the square root of 36m squared, 6m, that works. Square root of 100 is 10, so that works as well. So there's two perfect squares, they're subtracted. That means I can just follow this pattern for a difference of squares. Plug in the first term, 6m, plug in the second term of 10, make one addition and one subtraction, and we're done. For C, doesn't quite work. I have two terms here. Right? If I take the square root of 6x squared and the square root of 150, they don't give me nice numbers. Right? They're not perfect squares. Square root of 6 is 2.449, and then so on. So it wouldn't leave me a nice value. So right now I can't do anything except for common factor. So let's see if we can common factor anything. We should find that we can common factor a 6 out, which would leave me at x squared minus 25. Now if I go back and look, I should see that, oh wait, I still have a difference of two numbers, x squared and 25. Are those perfect squares? Well, if I go through and look, square root of x squared is x, square root of 25 is 5. Those are perfect squares. So I can actually factor the bracket out, still leaving that 6 there. X plus 5, x minus 5. So in some cases we may have to common factor first before we find a difference of squares, or before we use that pattern or relationship. The next thing we're going to look at is perfect square trinomials. So this is a little different. So again, we're going to go through and expand and then simplify to see the connection between these factors and the actual polynomial or expanded form, or trinomial in this case. So we did do some work with exponents or squares when using the distributive property. X plus 7 in brackets squared just means x plus 7 times x plus 7. Right? The entire bracket is squared. Now we can use our distributive property to multiply. X times x is x squared. X times 7 is 7x. 7 times x is 7x. And 7 times 7 is 49. I can collect like terms by looking at my two middle numbers. X squared plus 14x plus 49. So do we see any connection between this trinomial at the bottom here and this factored form up top? Do we see any connection between those two? If not, let's take a look at another example. 2x plus 5 squared. So again, same thing, 2x plus 5 times 2x plus 5. Distributive property. We end up with 4x squared plus 10x plus 10x plus 25. Collect our like terms. We end up with 4x squared plus 20x plus 25. Again, do we see any connection between these two values? Really what we're looking for is, do we see a connection maybe between these values here and the numbers that we get in the end? Because it's a perfect square trinomial, we're really not dealing with anything other than these numbers. So is there a connection between where we start and where we end up? We'll look at one more example. Again, 3x minus 5y squared is 3x minus 5y times 3x minus 5y. Distributive property. 9x squared minus 15xy minus 15xy plus 25y squared. Go back just to make sure. Yes, I wanted to make sure I had my signs correct on some of the other ones. Collect our like terms. End up being the two middle terms that we can add together. 9x squared minus 30xy plus 25y squared. Again, do we see a connection between these two, or between where we end up and where we started with. If you couldn't quite find a connection, that's okay. But the connection that you should have found, or maybe a pattern or a relationship, is that this first term, if we square that, we get the first term here. The second term, if we square that, we get the last term in our trinomial. And if we combine the two, or we multiply the two together, and then multiply it by 2 itself, we end up with our middle term. 3x squared, or 3x times 3x is 9x squared. Negative 5y times negative 5y is positive 25y squared. 3x times negative 5y is negative 15xy, but then times that by 2, and we get negative 30xy. So that kind of pattern is the same in all the other ones. So a perfect square trinomial can be factored like any of the other trinomials, whether it's a simple or tricky trinomial. But we can kind of save time if we recognize the pattern. So if we recognize that it's in these specific forms, so if we kind of recognize those values, or those numbers, or if we're told that it's a perfect square trinomial, we can quickly go through and factor it right away. Now, if you can't recognize that pattern, or can't recognize that it's a perfect square trinomial, that's fine, because you can factor it in the previous two methods that we learned. So let's go through and do a couple of examples. X squared minus 6x plus 9. Well, it's a trinomial. I can tell that right off the bat. How do I check to know if it's a perfect square trinomial? Well, let's take the square root of the first term, square root of the last term. Let's see if they're perfect squares. Well, the square root of x squared is x. The square root of 9 is 3. Now let's see, do we get, if we take 3 times x times 2, do we get our middle number? Well, we get 3 times 2 is 6 times x is 6x. So we do get our middle number. So we can see that this does fit here, and then this becomes that. So we do see that connection. We do see it fits that pattern. So if that's the case, we just plug in our two numbers that we found first, so the x and the 3. There's only going to be one bracket because it's a perfect square. And then we just throw in the sign from between the first and second terms. So in this case, a minus. So all we really need to do, we do need to find the square root of the first term and the last term if it does fit this pattern, because those are going to be the two values, not so much up here, but are two values in the brackets. We then multiply those two values together, and then multiply it by 2 to check to see if that middle value makes it a perfect square. If it does, great, we can plug in those two values in our bracket, and that negative, or that sign, tells us what sign should be in our bracket. So let's check the next one. 25y squared plus 20, that is a typo, it should be 20y, plus 4. Well, if I take the square root of the first term, 25y squared, that is 5y. The square root of 4 is 2. So those are perfect squares. So now we can do the last check. 2 times 5y times 2. 2 times 5 is 10. Times 2 is 20y. So we do get that these pair up. So this does work. Now, I'm going to have one bracket. It's going to be squared. The first square, or perfect square, is going to be the first, so 5y. The second perfect square is going to be second. And then this sign is going to go into the between them. Let's check this last example. So if I take the square root of 2 and the square root of 32, those don't work out to nice numbers. They're not perfect squares. So if they're not perfect squares, let's check to see if we can common factor. I can factor out a 2 from everything. So 2v squared minus 8v plus 16. So now this may look like a simple trinomial, so it may be easier for you to go through and solve it or factor it as a simple trinomial, but we can always do a quick check to see if it's a perfect square trinomial. Well, the square root of v squared is v, the square root of 16 is 4, and if we do v times 4 times 2, we get 8v. So these numbers do work out that it fits a perfect square trinomial. Again, if you don't like factoring it this way, you can always go back to the 2 previous ways to factor a trinomial. Because it does fit that pattern of a perfect square trinomial, we're going to have one bracket that's squared. We're going to take the 2 perfect squares, so v and 4, and put them into our brackets. And then the sign between the first 2 terms is going to be the sign in our bracket. So that is how we factor perfect square trinomials. Again, you're really using this to find that relationship just to make it a little bit easier to go through and factor, because by going through and finding those special cases, we can use the relationship between the expanded form and the factored form to quickly get to our answer. If you don't like these methods, that's okay, because then you can always go back and just factor them as simple or tricky trinomials like we've done in our previous lessons. So this is just kind of a quick way to go through and factor, not that you necessarily need to use these steps. There's just a little bit quicker to make things a little bit faster. But if, like I said, if you want, you can always refer back to the simple and tricky trinomial methods of factoring.